In this video, we're going to go over some practice problems from sections 4.3 through 4.6 in our textbook. Now, starting with section 4.3 here, we're looking at adding and subtracting polynomials. But before we do that, we're going to look at these 5 questions here. First, we want to identify some key characteristics of polynomial functions and classify them. So for questions 21 and 22 here, we want to write each polynomial in descending powers of the variable, then give the leading term and the leading coefficient. So looking at 21 here, we're going to write this in descending powers of our variable. So our first term is going to be the term with the highest power of our variable. So that would be p to the power 7 here. So this would be our first term. Our second term would be the next highest power. So that'll be minus 8 p to the 5th power, and then our last one here is our term with the lowest power of our variable p. So this is what this polynomial would look like written in descending powers of the variable. Now we also want to give the leading term, let's do some color coding, and the leading coefficient. Now the leading term when we're looking at these polynomial expressions is going to be the term with the highest power. So that's going to be this guy here, and it's always going to be the term in front when we have our polynomials written in descending powers of the variable. So in blue here, our leading term is going to be p to the power 7. Now, our leading coefficient is going to be the numerical value in front of our leading term. So in this case, this numerical value in front of p to the 7th power is just going to be 1. So we'll write this in green here. That would be our leading coefficient. All right, let's do the same thing for question 22 here. We again want to write this in descending powers of the variable. So the term with the highest variable power is going to be, or highest power of this variable y, is going to be 5y to the 4th power. So we're going to have 5y to the 4th power is our first term. Now our second term then is going to be the next highest power. That's going to be minus 2y cubed. And our last one is going to be 3y squared. Now again, our leading term is going to be the term with the highest power of this variable. So in this case, that's going to be 5y to the 4th power. It's going to be this entire term, but the coefficient is going to be this numerical value in front of our variable here. So in this case, that's going to be 5. All right. Now, for the next 3 questions, what we want to do is classify these polynomial expressions. So we want to identify each polynomial as a monomial, binomial, or trinomial. And if it's none of those, we're just going to say that it's none of these. And we also want to give the degree of each of these polynomial expressions. So for this first one here, notice we have the sum of 2 terms. So this tells us that this is going to be classified as a binomial. Now, the degree of these polynomials is going to be the highest power of our variable. So in this case, the degree of this guy is going to be 8. So we'll write degree 8 here. All right, let's do the same thing for this next one. Notice we have 3 different terms. So that means this guy is going to be a trinomial for 3 terms. And again, the degree is going to be the highest power that we have for this variable. So that's going to be this cube here. So our degree is going to be 3. Now for this next one here, it's a little trickier for 2 reasons. First, notice we have 1, 2, 3, 4 terms in this polynomial expression. And we actually don't have a word to classify polynomials of 4 terms. That's why we say that they are none of these. So none is going to be our classification in this case. And the second reason why this one's a little trickier is notice that each term, we have 2 different variables. We have p and q. So our degree in this case is going to be the sum of the powers of both of these variables, and it's going to be the highest one. So, for example, the sum of the powers of this first term is going to be 4 plus 1. So this would give us 5. This next one here, the sum of these 2 guys is going to be 3 plus 2, which also gives us 5. And then this next one, this p has a power 1, this q has a power of 3. Adding these guys together, that's going to give us 4. And then this last one here has 4. So the highest power in this case is going to be 5. So that means our degree of this polynomial is going to be 5. And we only do this when we are looking at terms that have 2 or more variables in them. Now, for these next 2 examples, we're going to be adding and subtracting polynomial expressions. So for this first one here, notice we're taking the sum of two different polynomial expressions here. And we have these parentheses around each one just to emphasize that this is the first polynomial and we're adding the second one to it. So I'm going to go ahead and drop these parentheses here. So I'm going to take my first polynomial expression and I'm going to add the second one to it. Now, when we are adding these polynomials here, we are combining like terms. So remember, a like term is one that has the same variable to the same power. So what we're going to need to do is identify like terms. So in blue here, I'm going to take this term that has this x to the fifth power. Now notice I don't have any other term that has an x to the fifth power, but so that's fine. Let's move on to this next term here. I have this minus 2x to the fourth power, and I also have this positive x to the fourth power. So those can be combined since these are like terms. They have the same variable to the same power. All right, let's keep doing this. Our next term here is x cubed, and I have a minus 3x cubed there. These guys are like terms because they have the same variable to the same power. And then lastly, I have this minus 1 and this plus 2 here. These are also like terms. They do have the same variable to the same power in that they don't have any variable. So these guys are just constants. They can be combined. So we still have this 2x to the fifth power. We can't simplify that any further, but we have minus 2x to the fourth plus x to the fourth. So that'll give us negative 1x to the fourth, or just minus x to the fourth. For this next one here, we have x cubed minus 3x cubed. So that's going to give us a minus 2x cubed. And then lastly, we have a minus 1 plus 2. So that's going to give us a plus 1. And this would be our final answer here. This is going to be the polynomial that we get when we take the sum of these two polynomials. All right. Let's do something similar for this next example here. Now, in this case, we're taking the difference of these two polynomial expressions. Now, in this case, we're also going to be combining like terms, but since we are subtracting this entire thing from this guy, this minus sign is actually going to need to be distributed to every single term in our parentheses here. So I'm going to emphasize that with these arrows here. We're distributing this negative sign to every single term, so it's actually going to change the sign of each term in those parentheses. So once I do that, I can drop the parentheses. So I'm going to do that for this first polynomial here. And then when I'm rewriting this one, I'm going to drop the parentheses, but make sure to change the sign of each of these. So I'm going to have a minus 4a squared minus 5a minus 6. Okay, now from here, we're just going to combine like terms just like we saw in the last example. Notice I have a 2a squared and a minus 4a squared. These are like terms because we have the same variable to the same power. I have a 3a and a minus 5a. These are again like terms. And then lastly, we have our two constants, minus 1 and minus 6. So combining these, I'm going to have a 2a squared minus 4a squared. This is going to give me minus 2a squared. Then I have a 3a minus 5a. So this will give me a minus 2a. And then lastly, I have minus 1 minus 6. So that's going to give me a minus 7. All right, so this is the polynomial that we'll get when we take the difference of these two polynomials. Now, subtracting these guys are very similar, or is very similar to adding these guys. We just have to do this first step here where we distribute that negative to each term in our parentheses. All right, so this brings us to section 4.5, where we're going to be multiplying polynomial expressions. Now, there's a couple different cases that we can see. For example, this question here, question 8, is one of the easier cases that we'll see when we're looking at the product of two monomials. So this is a polynomial here. This is a monomial because there's only one term, and this is also a monomial because we only have one term. And we're trying to find the product of these guys. So what we're going to do in this case is we're going to multiply our numerical values here. We're going to kind of group them together. So I'm going to have 5 times negative 4. And then we have our m variables. We have m cubed times m squared. And then we have our n's, n to the fourth power times n to the fifth power. Now, the reason why I'm grouping them together is because in this way we can kind of see how they're going to simplify. We know 5 times negative 4 is going to give us a negative 20. And then we know that m cubed times m squared can be found by taking the sum of these two exponents. So remember the product rule says that if we multiply two exponential expressions that have the same base, we can add their exponents. So this is going to become m to the fifth power. Similarly, n to the fourth power times n to the fifth is going to give us n to the ninth power. We're just taking the sum of their variables, or sorry, of their exponents. All right, let's look at question 13 now. Now, in this case, we're looking at the sum of two polynomials again. This first one is a monomial, and this second one here is a trinomial. We have three terms. Now, in this case, what's happening is this 6k squared term is multiplying everything in our parentheses here. So we're going to use our distributive property. So we're going to distribute the 6k squared to everything there. So let's write out what we have. We have 6k squared times 3k squared plus 6k squared times 2k plus 6k squared times 1. Now notice this first term is going to be the product of two monomials. So just like we saw in the first example here, we can multiply these numerical values here and these variables. So we're going to have 6 times 3, that's going to give us 18. And then k squared times k squared is going to give us k to the fourth power. Since we're multiplying these guys, we can add their exponents. Similarly, in this case, we're going to multiply our 6 and 2 for the second term. That's going to give us 12. And then k squared times k is going to give us k to the third power. Because this k here has this power of 1, and then we're going to add these guys together to give us k cubed. And then lastly, we know 6k squared times 1 is just going to be 6k squared. So this would be our final answer here. This is going to be the product of this monomial and this trinomial here. Now for this next example, we're trying to find the product of these two binomials. Now there's two different ways to do this, and the longhand way is going to talk about the FOIL method. Now the FOIL method is an acronym, and it tells us the order that we are going to multiply these terms. So we're going to multiply the first terms in our binomials, then we're going to multiply the outer terms. So the first terms would be these guys here, 3a and 3a. Then our outer terms are going to be this guy and this guy. So it's going to be 3a times minus 2c. So those are our first terms and then our outer terms of our binomials. Then I stands for our inner terms and L stands for our last terms. So this is the order that we are going to multiply all of these terms here to get this product of these two binomials. So doing that, we're going to end up with 3a times 3a. This is the product of our f here, our first terms. Then our next one is going to be 3a times minus 2c. So we're going to have 3a times minus 2c. Then this middle term here is going to give us 2c times 3a. So this is the same thing as 3a times 2c. And then our last term here is going to be 2c times minus 2c. So we're actually running out of room here. Our last term here is going to be plus 2c times minus 2c. All right, so let's go ahead and simplify this. 3a times 3a, this is going to give us 9 and then a squared. So 9a squared is going to be our first term. Now for the second term here, this is going to give us 3 times negative 2, which is going to give us a negative 6. And then we just have a times c. And then this middle term here is 3 times 2, which is going to give us 6. And then we again just have this a and c there. And then lastly, we're going to have 2c times negative 2c. This will give us minus 4c squared. All right, now notice we have a minus 6ac and a plus 6ac. So these guys are actually just going to go ahead and cancel out. And then this is going to give us 9a squared minus 4c squared, which is going to be our final answer. Now, like I mentioned, we are going to find this product two different ways. This was the first way using the FOIL method. Now, the next method is actually a little bit simpler. It saves us some steps, but in order to do so, I'm going to need to write down some equations. So I'm going to go ahead and do that. All right, so these are the equations from our textbook that we're going to use to find the products of these polynomials when we're looking at these special cases. So for this first one here, this is going to be the product of a sum and difference of two terms. So for any product of the sum and difference of two different terms, which we're going to call arbitrary x and y, it's always going to give us the first term squared minus the second term squared. So whenever we have the product of two binomials in this form, we can automatically write them in this way. And then we also have these two equations from our textbook, and this is going to help us with the next problem. So for now, let's focus on this one. So let's solve question 55 using this equation here. So again, if we're taking the product of a sum and a difference of two terms, x and y, this is going to be the first term squared minus the second term squared. So looking at this product here, notice that this is the product of a sum and a difference of the same two terms. Now, in this case, we're going to think of this 3a as our arbitrary x in this case. So this is going to be x. This is our first term when we're taking the product of this sum and difference. And then our second term, which we're going to call y, is going to be this 2c here. So essentially, we're just going to have x plus y and x minus y, and we're going to plug it directly into this equation here. So our first method was the FOIL, and our second method is going to be using this equation. So let's go ahead and write this out. 3a plus 2c times 3a minus 2c. What we're going to do is we're going to take the square of this first term. So this is going to be 3a squared, and we're going to subtract out the square of our second term. So this will be 2c squared. Now all we need to do is evaluate this. Using our second power rule, we know that the square is going to apply to both of these guys. So it's going to be 3 squared times a squared, which is going to give us 9a squared. And similarly, this square here is going to apply to both of these guys in this product. So we're going to get a minus 4c squared, which is going to be our final answer here. Now notice, using either method, we're going to end up with the same answer, but recognizing this for what it is, that it's the product of the sum and difference of the same two terms, easily allows us to find this product without having to do this long-handed FOIL method. So this brings us to our next example, where we're going to be looking at these equations. Now, again, these are directly from our textbook, and this tells us that if we have the square of a binomial, so in this first instance, we have the sum of two terms and we're taking the square, we're going to end up with this formula here. So we're going to have the square of the first term plus 2 times the product of the terms plus the square of the second term. On the other hand, if we're looking at the difference of these guys, so we're taking the square of a binomial where we're taking the difference of the two terms, we're going to end up with this version. The only thing that's changed here is that this middle term here is going to be negative instead of positive. So this is always going to be the case whenever we have the square of a binomial. So keeping that in mind, let's look at this next example. So for question 80 here, we have 3m minus 2 plus p. Now, at first, this might look pretty complicated, but notice we're just taking the square of two different polynomials. We're going to have this 3m minus 2 being essentially one polynomial, and this plus p being the other. So what we can do is we can treat these as their own individual terms. So I'm going to call 3m minus 2, I'm going to call this entire thing x, and this p, I'm going to call this y. And I'm calling them this in the same way that we called these guys x and y here, just to emphasize what our first and our second terms are. So going back up to these equations here, we're going to take the square of this binomial. That means we're going to end up with a polynomial of this form. The first thing that we're going to do is we're going to square this first term. So if this first term is 3m minus 2, we're going to take the square of that. So 3m minus 2, this entire thing is being squared because we're treating this entire thing as the first term. All right, now let's look at our second term here. This is going to be 2 times this first term x times the second term y. So this is going to be 2 times our x, which we're calling 3m minus 2, times our y, which is going to be p. And then lastly, we're going to take our second term in this binomial and we're going to square it. So that'll be p squared. All right, so now we have it in this form, but we need to expand on this. So we need to simplify it. Now notice here, we have 3m minus 2 and this is being squared. Well, 3m minus 2 is a binomial here. So again, we're taking the square of a binomial. So in this case, what we're looking at is the difference of two terms. So now we're going to use this equation in this example. So let's treat our 3m as our first term. We're going to treat this as x, and then minus 2 is going to be our second term, y. So using that second equation there, where we're looking at the difference of two terms, we're going to plug it directly into our equation. So treating this 3m as our first term in this guy, we're going to take the square of that. So this will be 3m squared. Then our second term here is going to be minus 2 times this product. So it's going to be minus 2 times the product of our first term and our second term. So this first term here and then our second term here. And then our last term in this equation is going to be the square of this term here. So 2 squared. So this entire thing, let's keep color coding, turned into this. Now we still have to deal with these guys here. So in order to simplify this, we are going to distribute this 2 to both terms in our parentheses here. We're going to end up with 2 times 3m gives us 6m, and then we have 2 times negative 2, so minus 4. Now notice we still have this p on the outside, so this p then is going to multiply everything in the parentheses here. So first we distributed this 2, and then now we're going to distribute this p to whatever product we got after distributing the 2. And then our last term here is going to be p squared. All right, so we're going to keep simplifying this. 3m squared is going to give us 9m squared using our second power rule here. Now this guy, we have a 2 times a 3m, so that's going to give us 6m times a 2. So this is going to give us minus 12m, and then 2 squared gives us 4. Now, like I said, for this guy, we distributed that 2 to both terms in our parentheses to get this, but we still have this p multiplying this entire thing on the outside. So this p needs to be distributed to everything in the parentheses here, giving us a 6mp minus 4p. And then lastly, we still have this p squared term. All right, now that's as far as we can go. We can't simplify this any further. We can't combine any like terms. So this would be our final answer for this one. All right, so that was a lot of steps here. Just to recap, we used both of these equations here in that example. We recognize that we started out with the sum of these two terms and we're squaring it. So we're taking the square of this binomial. So calling this 3m minus 2 our first term, treating that as our first term, we plugged it into this equation here. So we took the square of that first term, took 2 times the product of each term plus the square of our second term. And upon doing so, we again got the square of a binomial. We have a binomial here since we have two terms, but in this case, we're dealing with the difference of two terms. So we used this equation instead and turned this entire thing, the square of this binomial, into everything highlighted here, and then simplified as much as we could. Now, in this next example, we're again taking the product of two polynomials, but in this case, we're using function notation. So we have two polynomial functions, f of x and g of x, and we want to find their product. This fg of x here is the same thing as taking the product of f of x times g of x. So this is what we want to find. So let's plug in our known values. F of x is x plus 1. So we're multiplying x plus 1 times g of x, which is 2x minus 3. Now, in this case, we're not dealing with any special cases. This isn't the square of a binomial, etc. So what we're going to do is just FOIL this guy. We're going to multiply our first terms, then our outer terms, then our inner terms, and our last terms to get this product, and then simplify. So multiplying our first terms together, this is going to be x times 2x. So this is going to give me 2x squared. Then I'm multiplying x by minus 3x. So that's going to give me minus 3x. Next, I have 1 times 2x. So I have a positive 2x. And then I have a 1 times a negative 3. So this is going to give me minus 3. And then again, we just want to simplify it by combining like terms. Notice we have a minus 3x and a plus 2x, so we can combine those. We're going to get 2x squared minus x minus 3. And this is going to be our final answer. Now, in this next section here, we're looking at dividing polynomial expressions. Now, for example 9 here, we'll see that this is going to be our easiest case, and it's whenever we're dealing with monomials in the denominator. So what's happening here is we have this trinomial in our numerator and this monomial in our denominator. So this 5m cubed is dividing this, this, and this. So let's go ahead and write that. What we have is we have 15m cubed being divided by 5m cubed. Then our second term, 25m squared, is also being divided by 5m cubed. And lastly, 30m is also being divided by 5m cubed. So what we can go ahead and do is simplify each of these terms. 15 divided by 5 is going to give us a 3. And then we have m cubed divided by m cubed. That's just going to give us a 1 here. So this first term just reduces to 3. Now this next term here, we have 25 divided by 5. So it's going to give us a coefficient of 5. And then notice we have a m squared and m cubed in our denominator. Using our quotient rule for exponents, we know that we're going to be subtracting these exponents here. So this would give us 2 minus 3, which would give us a negative 1. And written with a positive exponent would just give us a m to the first power in our denominator. Let's move this over. So that would be our second term. Similarly, for this last term here, we have 30 divided by 5. So this is going to give us 6. Then we have an m by itself in the numerator and an m cubed in the denominator. So again, subtracting these exponents, we're going to get an m to the negative second power. And writing this with a positive exponent is going to give us m squared. So this would be our final answer here. We can't reduce or simplify this any further. Now, for our next example, we are going to be doing the process of polynomial long division. Now, definitely make sure you are going through the textbook and looking at the full procedure when doing so, but we're going to go ahead and use it for this example. So we have 3t squared plus 17t plus 10. So this is going to be in our numerator. So we're going to have 3t squared plus 17t plus 10, and it's being divided by this binomial 3t plus 2. So this is how we would write it out, just like a long division with regular numbers, but in this case, we're doing polynomial long division. Now, this process includes dealing with our leading terms. So we're going to do some color coding here. Our first step when dividing these guys is looking at our two leading terms. The leading term in our numerator is 3t squared, and the leading term in our denominator is 3t. So what we're going to do is go ahead and divide these guys. We're going to take the leading term in our numerator divided by the leading term in our denominator. We're going to end up with t by itself. Now, this result here is going to be the first term in our answer. So we're going to go ahead and put t up here. Now, the second step for this process then, just like with long division, is we need to subtract out a multiple here. And that multiple is going to be the result that we found in step 1, t, being multiplied by our denominator, this binomial 3t plus 2. Doing this product here, we know we're going to distribute that 2 to both terms in our parentheses. So we're going to get 3t squared plus 2t. And this is what we're going to subtract out from our numerator. We're going to subtract out 3t squared plus 2t. All right, so we know this minus is going to be distributed to this guy and this guy. So we're going to have minus 3t squared minus 2t. So these guys are going to cancel. And then we're going to have a 17t minus 2t. So that'll give me a 15t. And then we're going to bring down this plus 10. All right, now what we're going to do is repeat this process. We're going to repeat this process of dividing our leading terms. So we're going to look at the leading term in our resulting polynomial here. That'll be 15t. And we're going to divide by the leading term in our numerator. Just like we saw in step 1, we're going to repeat this two-step process here. So dividing these guys is going to give me a 5, and this is going to be our result, in which we write here above this divisor symbol. All right, now we're going to take that result of 5. Sorry, this should be step 3 here, and then step 4 we're also going to do in green, because again, we're going to take this result that we got in the previous step and multiply it by our divisor. So we're going to have this result of 5 and multiply it by 3t plus 2. Doing so, we're going to distribute that 5 to both terms in our parentheses. So we're going to get 15t plus 10. And this is what we are going to be subtracting out from our resulting polynomial. Now again, this minus is going to be distributed to both terms here. So we're going to have 15t minus 15t, and we're going to have 10 minus 10. So these guys fully cancel, and we're left with 0 or a remainder of 0. So this division then is going to result with the polynomial t plus 5. All right, so in the next two examples, we're again doing polynomial long division, but they're going to be a little more complicated than what we saw in the last example. Now, the reason being is because notice this polynomial has a degree 3. In the last example, our polynomial had degree 2. So we're going to do the same exact process that we saw. There's just going to be a couple more steps. Now, the first thing to note here is that this is actually a polynomial with a missing term. We're going from 3x cubed, so we have this cubic term straight to minus x. So this term here just has a power of 1. We're missing the term that has a power of 2. So what we need to do in this case is kind of include a placeholder when we're doing this polynomial long division. And we'll see why in a moment. So first, let's go ahead and write this in the correct form. So we're going to have 3x cubed. And then remember, we're going to have a placeholder, or sorry, this should be 3x cubed is our first term. And then, like I said, we're going to have a placeholder for our squared term, but in a different color. And then we're going to have minus x plus 4. And this entire thing is being divided by x minus 2. So again, we're going to repeat this process here. Our first step is going to be to divide our leading terms. So we have 3x cubed and x as our leading terms, and we're going to go ahead and divide these guys out. This is going to give us a 3x squared. So this is going to be the first term in our answer here. Now what we're going to do with this result is then multiply it by our divisor here. So we're going to take 3x squared and multiply it by x minus 2. This is going to give us 3x cubed minus 6x squared. And this is what we're going to subtract out from our polynomial in our numerator here. So we're going to subtract out 3x cubed minus 6x squared. Now again, this minus sign is going to be distributed to everything in our parentheses here. So we're going to have 3x cubed minus 3x cubed. So these guys cancel. And then in this case, notice we are going to end up with a positive 6x squared here. Now, this is why we have this placeholder, because when we're subtracting these guys, we're lining them up vertically. So it's nice to be able to see what's happening with our x squared terms. In this case, we have 0x squared, and then we are adding 6x squared to it. So this is just going to give us a positive 6x squared. And then we're going to bring it down everything here. We still have a minus x and a plus 4 in this polynomial. Now, again, we're going to repeat this process. In this third step here, we're going to look at the leading term in our resulting polynomial, 6x squared, and divide it by the leading term in our divisor. So we're going to have 6x squared divided by x. This is going to give us 6x. And we're still repeating this process, that 6x is going to be multiplied by our divisor here, and that's what we're going to subtract out. But don't forget, whenever we're dividing these leading terms, that result is going to become part of our answer. So we're going to go ahead and keep track of that by putting it up here. So we have a plus 6x. Now going back to step 4 here, we're going to multiply the 6x by our divisor. So we're going to get 6x squared minus 12x, and that's what we're going to subtract out from this resulting polynomial. So we're going to subtract these guys. These guys are going to cancel. And we're going to have a minus x and then a plus 12x. So this will give us a positive 11x as our result. And then we're going to bring it down this constant of 4 here. And then we're going to repeat this process. So for step 5 here, we're going to do this in blue because we're again looking at our leading terms. We're going to divide these guys. 11x divided by x gives us 11. So this is our result, which is going to go up here. And then we need to take that result and multiply it by our divisor. this is what we're going to subtract out. So we're going to subtract out 11x minus 22. All right. Subtracting this from this resulting polynomial here, these guys are going to cancel. And we're going to have 4 and then plus 22. So this is going to give us 26. Now, this case, or in this case, this is going to be our remainder. We can't divide out any further. This is our stopping point. So what we're going to do then is write out our final answer. It's going to be this resulting polynomial plus this remainder. And we write this remainder in a special way. So let me go ahead and write this out. We took 3x cubed minus x plus 4, and we divided it by x minus 2. When we did that, we got the resulting polynomial of 3x squared plus 6x plus 11. But we have this remainder of 26. And we write this remainder as, we're going to add it to our resulting polynomial. We're going to add 26 divided by our divisor. So this would be our remainder quantity, and this is how we'll write our final answer. Everything in the box here is going to be the polynomial that we got plus the remainder that we got over the original divisor, x minus 2. So this would be our final answer for this case. Now for this last example, we are again going to be dividing two polynomial expressions, but in this case, we're dealing with function notation. So we're given this function f of x and this one g of x, and we want to find this. So we want to divide these guys. F divided by g of x is going to be the same thing as f of x divided by g of x. Now plugging in our functions, we're going to have 8x cubed minus 27 as f, so that's going to be in our numerator. Then in our denominator here, we're going to have g of x, which is 2x minus 3. So this is the division that we need to perform. So let's go ahead and write this in our long division form. But keep in mind, we jump from a cube term to a constant term. So we're actually going to have two terms missing, our squared and our x term. So we're going to have to include two placeholders in this division. So we're going to have 8x cubed plus 0x squared plus x minus, sorry, this should be plus 0x minus 27. Okay, so these are our two placeholders here so that it's easy to subtract out our result. And we're dividing this by 2x minus 3. So let's repeat the process that we've seen in the last two examples. Let's move this over so we have enough room. For our first step here, we're going to take this leading term and divide it by this leading term. We're going to have 8x cubed divided by 2x. This is going to give us a 4x squared. So this is going to be the first term in our solution. Now we're going to take this result and multiply it by our divisor. Doing so, this is going to give us 8x cubed minus 12x squared. This is what we're going to subtract out from our function in the numerator. We're going to subtract out 8x cubed minus 12x squared. These guys are going to cancel. And then we're going to have 0x squared plus 12x squared. So we're going to have a 12x squared, and then we're going to bring down these two terms, plus 0x minus 27, and then we're going to repeat the process. We're going to take the leading term in our resulting polynomial and divide it by the leading term in our divisor. So we're going to have 12x squared divided by 2x. This is going to give us 6x. Now that result goes up here. It's going to be our second term in our solution. Then we're going to take this result and multiply it by the divisor. So 6x times 2x minus 3. This is going to give us a 12x squared minus 18x. So we're going to go ahead and subtract that out from this guy. All right. These 12x squareds are going to cancel, and then we're going to end up with a positive 18x. And lastly, we're going to bring down this minus 27, and then repeat this process for a third time. So we're going to take our leading terms here. This is going to be 18x divided by 2x. This is going to give us a 9. And this is going to be the third term in our solution. So we're going to have a plus 9 here. We're going to take that result of 9 and multiply it by our divisor. We're going to get 18x minus 27. So this is what we're going to subtract out from this last resulting polynomial. We're going to subtract out 18x minus 27, which we're going to see that these guys cancel after distributing that negative, and so do these guys. So our remainder in this case is going to be 0. So our final answer, let's move this over, when dividing these two polynomial functions is going to be 4x squared plus 6x plus 9. Now, lastly, we also want to give any x values that are not in the domain of the quotient function. So the quotient function is going to be this guy here. So we want to find the domain of this guy. Now, remember, when we're looking at the domain, we're going to assume that it's going to be all real numbers except those that make our function undefined. Now, whenever we divide by 0, that's going to be undefined. We can't ever divide by 0. So what we're going to do is we're going to set this denominator equal to 0 and find which values will make that statement true and then exclude them from the domain. So we know that our denominator cannot be equal to 0. That would make this undefined. So we need to find the values that will make it equal to 0. So 2x minus 3 is equal to 0. We're going to solve for x. We are going to add 3 to both sides of this equation and then divide by 2. So x is then going to be 3 over 2. So this value of x is the value that'll make this denominator equal to 0, this 2x minus 3 equal to 0. So that means we're going to exclude this x value from our domain. So we're going to exclude this x value from our domain, and in interval notation, this is going to be everything except 3 over 2. So we're going to go from negative infinity up to 3 over 2, and then from 3 over 2 up to infinity, to emphasize that we're excluding this value from our domain.